Hello everyone and welcome back to Nunley Math. Thank you so much for joining us here today as we look at the last of our methods for solving systems of linear equations. If you've been following along with us, you know that we've already explored solving systems by graphing and solving systems by substitution. We are going to review those very quickly today, but then we're going to look at the last method, which I think is actually one of the coolest methods for doing this. I think it's got some neat mathematical substance behind it and allows us to do some really interesting things. So without further ado, let's go ahead and get started here. As always in my class, I like to start my students off with a quick review of things they should already know that relate to what we're doing. This first example asks them to solve a system of equations using the graphing method. If you have a paper and some grid paper with you, I'd recommend pausing the video and trying this on your own and then restarting the video to see if you've done it the way I'm doing it and to check your answer. I'm going to assume you've already done that, and I'm going to go ahead and graph these for you. Notice that our first linear equation is x plus 2y equals 7. It is in standard form, so I think I'm going to go ahead and solve this or graph this using intercepts. Remember, when we graph using intercepts, we alternately substitute a 0 in for x and a 0 in for y and solve to see what we get. If x was a 0, this part of the equation goes away, leaving me with 2y equals 7. I would divide both sides by 2 and get the 3.5. Likewise, if I put a 0 in for y, 2 times 0 is 0, leaving me with x equals 7 on its own. So I go to graph those. There's the coordinate 7, 0. Here's the coordinate 0, 3.5. I don't like to do decimals when I'm graphing because I'm always afraid I'm going to be slightly off and it's going to mess things up. So what I noticed here is that I've gone down 3.5 and right 7. I'm going to continue that pattern up the other direction. Up 3.5 puts me at 7, and I'm going to go backward 7 and get my other dot here. I feel a lot more confident now that I have 2 points that are actually integer coordinates. That makes me feel pretty good about where that line is drawn. My second linear equation is not in any known form, but I can change it pretty easily to slope-intercept. Remember, slope-intercept has a y by itself equals mx plus b. So I'm going to need to move this plus 4 to the other side using property of equality, subtracting 4 from both sides. That's going to give me y equals x minus 4. Remember, if I have y equals x minus 4, your slope is the value in front of x. That's 1. Your y-intercept is this value that's off here by itself, this minus 4, which is the coordinate 0, negative 4. So I start off at 0, negative 4, and I go up 1, right 1. Up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, and I get this line. Hopefully you can see that the two lines cross at the point 5, 1, which means that 5, 1 is the solution to the system. Of course, if I were to plug 5, 1 in here, 5 plus 2 times 1 does equal 7, and 5 does equal 1 plus 4, showing that I do indeed have the correct solution. Our second example is using the substitution method. Once again, I'd recommend pausing the video, trying this on your own, and then restarting it to see if what you've done matches how we do it. Notice that I have in this system one equation in standard form and a second equation in slope-intercept form. When we use the substitution method, it's very important that you have one of these variables by itself, or in this case, we have the y by itself. Now, I prefer to think of this way. If I have y equals 2x plus 7, it means that whatever value I have for y has the same value as 2x plus 7, or these two are the same thing, meaning anywhere I see a y, I can replace it with a 2x plus 7 without changing the value of the solution. So I'm going to take this first equation, the 4x plus 3y equals 31, and I'm going to look for where that y is. Notice that y can be replaced with 2x plus 7 at any point in time. So I'm going to take this y out and replace it with a 2x plus 7. Notice everything else is still the same. I still have the 4, I still have the x, I still have the plus, I still have the 3. The only thing that's changed is I've replaced that y with 2x plus 7, and it equals 31. The reason we do that is because now this is a single variable equation. We should be very, very good at solving those at this point. So I'm going to do that quickly using my distributive property. Using the distributive property again to combine like terms, using my property of equality to subtract 21 from both sides, and the property of equality to divide both sides by 10, giving me an x value of 1. Once I know my x value, I can then take either one of these two original equations and I can plug a 1 in anywhere I see an x. It doesn't matter which of these two equations you pick as long as it is it's the easiest one for you. For me, it seems easiest to solve y equals 2x plus 7. Once again, I'm going to replace the x with a 1, so that x comes out, the 1 goes in, and I simplify and get a 9. My coordinate, 1, 9, is the solution to this system. Notice 4 times 1 is 4, plus 3 times 9 is 27, 4 plus 27 is 31. 2 times 1 is 2, plus 7 does indeed equal 9, so I know that that is correct. Hopefully those two problems were pretty straightforward for you. If not, I do recommend you go back and watch our video on solving by graphing and solving by substitution. Those are not our focus here today. We're just reviewing those to keep them fresh in our memory. I want to show you something really cool that's going to lead us to our third way of solving systems. I think you're going to like this. This is kind of awesome. It goes like this. 8 plus 3 equals 11. I know that's mind-blowing, right? 8 plus 3 equals 11. That's not actually the cool part yet. Let me keep going. 4 plus 5 equals 9. Once again, that is not entirely mind-blowing, but it is a nice setup for what we're going to do next. Let me keep going. 12 plus 8 equals 20. That actually is very, very cool. If you don't think so, you're probably not seeing something. I would recommend pausing the video, looking at that for just a couple minutes, and see if you can figure out what is so cool or interesting about that. I am going to go ahead and go because this is a video and we don't want to sit here with 2 minutes of dead silence. But hopefully what you've realized is that this last equation is created by adding these first two equations together. In fact, you might be able to see it a little more easily if I put that line there. Notice 8 plus 4 is 12, 3 plus 5 is 8, and 11 plus 9 is 20. A very, very important mathematical principle here, and that is this idea that when I'm adding things together, all I'm really doing is combining things. So if I have an 8 and a 3 and a 4 and a 5, if I have a pile of 8 of something, a pile of 3 of something, a pile of 4 of something, and a pile of 5 of something, and I were to combine that all into one big group, it's going to give me a sum of 20 of whatever those items are. Now, I can take that 8 and that 3, if I think of these as being piles, and I can combine those two piles into a pile of 11, and I can combine the 4 and the 5, these two piles, into a pile of 9. And if I do that and combine them into a pile of 11 and a pile of 9, and I look at those all together, it's still a sum of 20. Alternately, instead of putting the 8 and 3 together to get an 11, the 4 and 5 together to get a 9, I could combine the 8 and the 4 to get a 12, and my pile of 3 and 5 to get a pile of 8, and now I have two piles, one 12, one 8. If I look at those together, though, it's still a sum of 20. Now, if I take my pile of 8 and 9 together, I get a 20. If I take my 12 and 8 and put them together, I get a 20. I could have this all as one big pile of 20. Notice, it doesn't matter how I split these piles up. 20 of something is always 20 of that thing. And this gives me a lot of flexibility in terms of how I think about the items that I'm adding. Now, certainly there are other ways to divide these. I could take my 8 and pull one off and make it a 7 and a 4. I mean, there's a lot of things you can do here. But what I want us to notice today is this. If I take these 4 and combine them, I get 20. If I take the rows and combine them, I get 11 and 9, which is 20. And if I take my columns and add them together or combine them, I get 12 and 8, which is also a 20. I am just rearranging my information in very different ways. How does that lead us to solving systems? Well, consider this. If I have x plus y equals 5, and I have x minus y equals 1, I can set those up in the exact same way I set up the problem on the last slide, where I write those as an addition problem. Notice that if I were to add vertically instead of adding horizontally. Horizontally, I get a 5 and a 1. Vertically, though, I'm going to get a 2x, and I'm going to get no y's, and I'm going to get a 6. If I think of this the same way I thought about my last slide, all 4 of these together have to have the same value as these 2 together and as these 2 together, and any of those sections is going to have the same value as a 6. But there's an advantage to this row right here. Do you see what it is? I have x's and I have no y's. This is a single variable equation. Using this single variable equation, I can solve to find the value of x, which in this case is a 3. Notice that's very different from the substitution method. In the substitution method, I had to have one of these variables by itself. This method actually works the best if my numbers or my linear equations are in standard form. But just like the substitution method, once we know the x, we can pick either one of these equations, plug that x in, and solve to find y. Your solution is the coordinate 3, 2. 3 plus 2 equals 5. 3 minus 2 equals 1. There again, that's a third method. Now, sometimes we're going to like one method better than the other. Sometimes you'll want to do this by graphing. Sometimes you're going to want to do this by substitution. But if you already have things that are in standard form, probably the addition method, or sometimes it's referred to as linear combination, is the easiest. Take a look at this example. I have 3x minus 3y equals 24 and 3x plus 3y equals 12. I rewrite those, and just like before, I'm going to add those together. 3x plus 3x makes 6x's. Negative 3y added to 3y makes no y's. I bring down my equal sign. 24 and 12 make 36. Just like before, all of these have the same value as all of these, has the same value as all of these, has the same value as this over here. The advantage of this third equation is that we have x's and no y's, which means we can solve this. X is a 6. Just like before, once you know that x is a 6, you can pick either of these equations, plug that 6 back into that equation, and solve to find your y. In this case, you get 6, negative 2. If I plug in a 6, I get 18. If I plug in a negative 2, I get plus 12, or plus 6. 18 plus 6 is 24. 3 times 6 is 18, plus this would be a negative 6. 18 plus negative 6 is also 12. This does, in fact, work. Now, this example is slightly different from the others. Can you see what the problem is? Notice that if I were to try and do this with linear combination, I would get 3x's plus 6y equals 15. I'm still using linear combination, and each of these sections is still equal to all the other sections, but we've got a problem. None of our variables disappeared. I can't use this method if I can't get one of the variables to disappear. But I do notice one thing. I have a 3y and a 3y lined up right here. Those don't go away, but they do give me an idea. Let me erase this from my slide. They do give me an idea. If I were to use my property of equality, which says I can do anything to an equation I want as long as I do it on both sides, and I were to multiply this second equation by a negative 1. Remember, I have to do it on both sides. If I were to multiply that by a negative 1, the first equation would stay the same, but the second equation would change. It would become negative x, if I pass this out over here, negative 3y, and negative 7. What's the advantage of that? Well, now 2x minus x, or plus negative x, is x. And notice 3y and negative 3y now become a 0. I didn't bother to type it in this time. And you have, at the end, 8 plus negative 7 is a 1. We can use the property of equality to force our system to have a set of numbers that are opposites from one another. We like those opposites because that's what gives us that plus 0. As always, once you know what the 1 is, or what the x is, we can pick either of our original two equations, plug that 1 in for an x. I picked the first equation this time. Plug that 1 in for x and solve for y. Notice when x is a 1, y is a 2, we have the solution 1, 2. Now we could check that if we wanted to, but for the sake of time, I'm going to skip over that and just keep going. Here's another example. Notice that if I add 3x and 5x, it doesn't go away. If I add negative 6 and negative 3, it doesn't go away. But I can, once again, use my property of equality. My goal is to try and make either my x's be opposites of each other or my y's. Do you have any idea what you might do there? I'm going to go through and multiply that second equation by a negative 2. Because when I do that, my first equation remains the same, but my second equation becomes negative 10x, positive 6y, and negative 28. So that when I add those together, I get negative 7x, my y's go away, and it equals negative 35. I divide both sides by negative 7, x is 5. As always, I can take this and I can substitute that x back into either equation. In this case, I chose the first one. I plug a 5 in for x. 3 times 5 is 15. I'm going to subtract 15 from both sides and get negative 22. Divide both sides by negative 6, and I get 22/6, which is 3 2/3. And you can see my, my pop-ups are in opposite order there. So your coordinate is 5, then 3 2/3. Sometimes we do get messy numbers like that. It's not always fun, but it's not too bad. Remember, if we were graphing, it would have been almost impossible for us to have found that 3 2/3. I believe I have one more of these for you. Check this one out. Can you think of a way to either make the x's opposites or to make the y's opposites? I'd recommend pausing this and thinking through that for a second. See if you can come up with a method. Otherwise, I'm going to go ahead and move on. There are several options here. The one I find the easiest is to multiply through that first equation by a -5 and the second equation by a +3. Remember, I can multiply through by anything I want. There's nothing that says I just have to multiply the second or the first. I can multiply them both by something to create entirely new equations. The first equation becomes -5 times 3 is -15 minus 25y equals -150. The second equation becomes 15 plus 24 plus 147. Notice -15 and +15 are opposites of one another. That means they're going to go away. -25y plus 24y makes -y equals -150 plus 147 is -3, making y a 3. As always, once you know your y, you can select either of these equations. I happen to pick the first one. I plug in my y, I simplify, subtract 15 from both sides, divide both sides by 3, you get x is 5. Your final solution is 5, 3. Here again, if we had more time, I could substitute those in and simplify to see and prove that they are true, but we're not going to take time to do that today. Hopefully you found this helpful and useful. As always, make sure you smash that like button. My students told me I need to phrase it that way. It'll make me more popular. Smash that like button. Make sure you leave me a comment. Turn on your notifications. Make sure you subscribe so you can follow along with us as we work our way through Algebra 1. If you have any thoughts for improvement or any suggestions or just want to leave us a comment, please take the time to do that down in the comment section. As always, we wish you the best of luck. You guys take care, okay? Bye-bye.